Welcome to my video number 7 on the energy series. In this video, I want to talk about conservative and non-conservative forces. Forces fall into these two basic categories. A conservative force is one whose work depends on the initial and final positions, not on the path. So that's the basic definition of that. So what would be an example of that? Be like gravity, think about the potential energy on the Earth. It depends on the height. The potential energy is equal to mgh. So it depends on the height, not really how you got to that height. You can move there, jump up and down and get there, but it's just the height difference. So that's an example of a conservative energy or force. Also, we've got like Hooke's law, or the springs. And that tells us that the force is equal to the minus some constant times the position, or the change in position. And so what that is, if you have a spring attached to a wall, or a rigid mount, and you put force on it, this force is just proportional to how far you stretch the string. If you stretch the string this way, it takes more force pulling it back. If you push it together, it pulls that way. So it's just a delta change in the position. It doesn't matter how you go, how fast you go. So for a conservative force, the kinetic energy initial plus the kinetic energy the potential energy initial is equal to the kinetic energy final plus the potential energy final. So for these forces, conservative forces can store potential energy. Like in the spring case, or in the gravity, or distance from the sun, or from the center of the earth. So that's one major class, conservative forces. Now, don't get that confused with conservation of energy, because that's a related concept, but this is a type of force. Next, we want to talk about, let's look at an example. Conservative force, a box moved to a high shelf. I talked to him just a minute ago about that. Here's your shelf. And then here's the individual shelves on the shelf. It's kind of a side view. So here's your box. And if you want to move the box up to there, this is going to be your change in height. So we know the potential energy associated with that. The change in potential energy is just the mass times gravitational potential times the height difference. It does depend on how you do it. You can lift it one stair at a time, one shelf at a time, or you can walk over here and come back. So it doesn't depend on the path and how you got there. So it only depends on the change in position. In this case, it's the change in height. Now we want to talk about non-conservative forces. A non-conservative force, the work done depends on the path chosen. So examples of this be like air resistance. If you say you're in your car and you want to go from point A to point B, you have certain air resistance if you go directly there. But if you take a kind of a curvy path or circuitous path to get there, you experience a lot more air resistance because your path is actually longer, even though the point you go from point A to point B. And then also friction. You're going to have a lot more frictional energy being dissipated in the tires and all the bearings and the energy itself, plus all the fuel you're expending. So that's an example of a non-conservative force. So in this case, energy is transformed into, and in the case of the car here, it's thermal energy, We're expending more fuel to move the car, and that if the longer the path, the more fuel we expend. That it does depend on the path chosen. And we also have sounds being generated, the motor running, the tires, and all the sounds associated with a car. This is a non-conservative force example. Then also the deformation of materials. That'd be like the tires are squeezed and expand, so you're putting energy into that elastic properties of the tires and bending of the metal slightly as you go over bumps. So this is an example of a non-conservative force. So what we can say is the total energy in the system is conserved. We always know that. This is where the word conservative and conserve kind of get confusing, but total energy in a system, that's one of the laws of nature. Energy is conserved. But in this case, the words are a little confusing, non-conservative and conservative. So that's always conserved. But in the case of a non-conservative force being involved, the kinetic energy initially plus the potential energy initial does not equal the kinetic energy final plus the potential energy final, because you've got all these other forces like friction and air resistance and thermal and sounds and deformation of materials that absorb some of that energy and dissipate it in forms that really you're not really interested in traveling just from A to B. So that's different. This is a non-conservative force, and I'm going to do an example next on that. Our example here would be of a non-conservative force. We've got a 1,200 kilogram car. It's traveling at 20 meters per second. Then the driver brakes to a stop. So we want to find out the initial kinetic energy, the final kinetic energy, and we're going to see that these two don't add up, and we're going to see where did this energy go. So for part A here, the kinetic energy initial is equal to 1/2 mass velocity squared, and that's equal to 1/2, and then the mass of the car is 2,000 kilograms, velocity is 20, and that's meters per second, quantity squared. That turns out to be 240,000 joules. I just did the math for you. We can say that's 240 kilojoules. That's how much energy the car possesses due to its mechanical motion when we apply the brakes. Now, at a stop, when we stop, the velocity is equal to 0, right? So the kinetic energy final is equal to 1/2 m0 squared. So we know that's just 0. So when we stop the car, there's 0 kinetic energy. So we've gone from this kinetic energy to this kinetic energy from 240 kilojoules, which is quite a lot, to 0. All right, if we're on a flat surface, our potential energy hasn't changed. So where did the energy go? And so let's think about where did that energy go. So it went to heat in the brake pads. If you ever felt brake pads after the car is braked, they get hot. You don't want to touch them because that's where the energy goes in those brake pads. And then the brake, all the mechanisms around the brakes, usually called the rotor, that absorbs a lot of the energy, gets hot also. And then when the tires get hot because you're moving, and then you're applying pressure to those tires, frictional force against the road, that causes heat to go into that. And then we're also transferring energy into the road. And there's also going to be sound, especially if you apply the brakes rapidly, because you're moving air. So there's air resistance also. So it goes to moving some of the air out of the way. But the total energy is conserved, because your energy didn't get transformed from kinetic energy, it got transferred to this energy. So your kinetic energy initial plus your kinetic energy final plus the energy that goes into all these other forms is conserved. So total energy is conserved, even in the case of a non-conservative force. Well, I hope you learn a little bit about conservative and non-conservative forces. It's an important concept in physics. I want to thank you for watching.